Next problem. This one looks kind of interesting. We have the triangle ABC. Omega 1 passes through B and is tangent to AC at A. So the way I usually do this, because I've done this a bunch of times on my channel, kind of like this. So we draw the perpendicular to AC through A, and we let it meet the perpendicular bisector of AB at a point. And that's the center of that circle. And then we do the same thing in the other direction. All right. And so we draw that circle. And so that's tangent to AB at A. Okay, so these are our two circles. And it looks like they form if I construct it this way, so yeah, so if this point is like the circumcenter of ABC, so I'll call it O, then this is a parallelogram, because DO is perpendicular to AB and AE is perpendicular to AB. All right, so I'm gonna hide a bunch of stuff. So yeah, we have a little parallelogram here. They intersect at D. Oh, we already used D, so let's call it something else. We call this one F. The Dumpty point. Maybe it is the Dumpty point. I'm not sure. So the Dumpty point is the harmonic conjugate. I'm sorry, is the isogonal conjugate of the Humpty point, right? From what I know. Oh, we already used E too, so I got to change this to G. Okay. That's the only thing I know about the Dumpty point, is that it's the Humpty point is the perpendicular from the orthocenter to the median. So there's really three Humpty points. So if you take the orthocenter to the median from A, that's the A Humpty point. And then if you take the isogonal conjugate of that, that's the Dumpty point. And it's supposed to have some other very nice properties, which I don't know too much about. But I know more about the Humpty point. So, all right, so we want to let AD meet the circle at a point E. Let's shrink.
We just want to show that OD is perpendicular to AD, basically.
Oh yeah, that OD is perpendicular to AE. Yeah, that would.
Oh, does that mean symmedian?
Maybe it might be related to the symmedian. Let's try it. So, where's my midpoint? Here we go. So let's see if it's the median. It looks like there's a good chance it is. Yes. So we want to show AD as a symmedian. That solves it. Wait, how do we know it's a symmedian? I don't see it right away.
Angle chase, because we know BAD is equal to DCA and something like that.
So BAD, if we know D is the Dumpty point, so the Humpty point, yeah, it's isogonal to AH, but we need one more isogonal, right? Like, we need to know it's isogonal with one of the other lines, I guess. You heard of Humpty and Dumpty points for the first time. Okay, but Anmal still solved it, and he's never heard of Humpty and Dumpty. So let's see, or at least I think, or Anmal, do you think he solved it? So, yeah, I'm still not sure Hmm. Okay.
In this just angle chase now, we know everything here that BAD is DCA, which is half of DGA.
Wait, so how do you know AB is a symmedian? Is that just angle chasing? Since AD is a symmedian, how do we know AD is a symmedian? You guys are light years ahead of me. So I guess angle BAD is equal to angle ACB. Wait, is equal to angle ACD. Okay, so yeah, I'll construct the Humpty point. Isn't it fun using fancy words? So that's the median. Yeah, we should probably call this one H, not the other one. All right, so that's H. And this is M. And if we take the perpendicular, so actually, I'll do it this way just because I'm lazy. So a property of the Humpty point is that it's cyclic with BH and C. So I don't want to call it I, I'll call it J. J is the Humpty point. You saw the Dumpty point? I've never done a Dumpty point. I've only done a Humpty point. Or maybe somebody else talked about it. I'm not, maybe it was like Urijan, I think. So J is the Humpty point, and we claim D is the isogonal conjugate of J. Is that obvious? Okay. Let's see. So is that, so angle ABJ is 16.7, and angle CBD, yep, it is the Dumpty point. So BCOD is cyclic. Okay, so that's a property of the Dumpty point, I'm guessing. Oh, can we use Michel's theorem here? I'm wondering. So yeah, Rodrigo, how do you know? I guess it's just an angle chase that BCOD is cyclic, right? Because angle BDC is basically 360 minus BDA minus CDA, right? So yeah. And once we know that, okay, so basically we want to show OM and AE concur on that circle. Feels a little like the radical axis theorem, doesn't it? Yeah, so can we show OM and AE concur on that big circle? J is the reflection of E across BC. Yeah, so that I know. Wait, but is that obvious that J is the like if J is the
Then J is equal to EMB, and that is the I guess property of symmedian, and it proves that A is symmedian.
So you said JMB equals EMB is what you said, right?
Yes, that's enough to prove that A is symmedian.
So how do you know that angle JMB is equal to angle EMB?
No, I don't know that, but you said that J is the reflection of E.
Oh, yeah, Hakan. Oh, I was reading what Hakan said. So, like if we know AE is a symmedian, then I know that's true. But I don't yet know AE is a symmedian. Isn't it the property of the Dumpty point that AB is the symmedian? If we know D is the Dumpty point, but I don't, how do you know D is the Dumpty point? Oh, are you just saying that's a property of the Dumpty point? Ah, okay. I think it's not hard to prove actually by an angle chase. So I'm just trying to think how to do it here, but if we can show angle DBC equals angle ABH, that would solve it. So let's see. Can we show DBC equals ABH? That's the same as saying DBC equals ACH. Feels kind of like.
Let's the points on BC, the second intersections of these two circles, and then we have some similar triangles, and I guess we can find DBC from there.
Angle DBC.
We first need to label these intersections of omega 1 and omega 2 with BC.
With BC. Okay, so like that and that, right?
So now DBC is DBI, which is DAI, and I think CAI should be similar to CBA.
Okay, so DBI is DAI. And you think, let's see. So is ADI similar to ACH is what you're saying? ADI and ACH?
Yeah, that's similar because of the tangency at A.
So what are the two triangles? So, say the two triangles again.
CIA and CAB.
Add
It follows by power of point that CI times CB CA squared.
DIA or
CAB.
So CAB, and what's the other one? DI.
No, I'm not talking about D right now. I'm just saying that angle AIC should be angle A.
Oh. AIC is similar to ABC.
And I guess this means that DIA is 180 minus angle A. So, wait, that's obviously no.
Okay. So DAI is DIC. So DBI is DAI. Okay, I think I get what you're saying. So there's just a lot going on here. So DAI is angle B minus angle CAD. I've seen that before. Yeah.
Isn't angle OFA equal to angle A?
Yeah, okay.
We know angles here, so I guess we can find angle BAD. You know, this proves that this is symmedian, of course.
Sorry, there's so many things happening that it's so BAD is equal to angle DIC. Okay, I'm just gonna start. Yeah, type it out in the chat step by step. Yeah, I think there's like we have like a bunch of ways of solving this problem, but yeah, type out the way you were thinking in the chat, just so it's easier. Or I was thinking animal, but either of you could do it. It's fine. So FAB is 90 minus A. So ADO is angle A. Oh, I'm sorry. AFO is angle A. Okay. So AFO is angle A. So then we can find angle BDA. How do we? Because if we know FAB, then we can know ADB. Okay, so I know. Okay, so FAB is 90 minus angle A. So yeah, AFO is angle A, and then angle BDA we can find. I agree with all that so far. I agree we could figure out angle BDA. And so then you're saying, yeah, I think it is trivial with. I think I've seen an article before that talks about that center of spiral similarity. But yeah, I'm just trying to prove it now, just for the people that haven't seen it before. Oh, really? Ah, nice. I just want to prove it on my channel for now. I love Osmond Now's channel, though. Let's see. All right, so let me think about this for a sec. I mean, really, I think, so if we label these points, these are like L and N. I mean, we want to show ANDOL as cyclic, right? That's another way to solve this.
We already know ANOL is cyclic.
Right, we know ANOL is cyclic. If we can show D also lies on that, that would solve the problem. And maybe that's like the, so it looks like ND and K I think I'm not sure if that's actually true. ND and K. Oh yeah, ND passes through K. What is K? I don't even know what K is anymore.
K is the intersection of omega 2 with BC. Well,
so
if
and okay. So yeah, maybe this is like
okay, can we prove this now?
yeah. Let's see. Yeah, I'm just trying to find the easiest way to do this. And that, but yeah, I think if you know that thing on the spiral similarity, I think that would solve it. But let's see. Yeah, I just want to take this step by step.
NDK can be proved collinear because we know NDA is equal to NAD.
NDA.
Do we know that or don't we?
I don't think that's true. No, NDA is not NAD. So
By the way, are we done if we assume NDK collinear? I guess that's easier to follow.
Yeah, if we assume ND and K are collinear, it's almost like, yeah, we want to show NDOL is cyclic. So we want to show NDL is equal to NOL. And NDL
Yeah, NOL is just FOG, which is FAG. And I guess we can find IDK as IDE, which turns out to be IBA.
Yeah, NOL is 180 minus A, right? NDL.
Yeah, if we prove that NDK and LDI are collinear, then NDL would be IDK, and we know IDK is IDE plus KDE, and IDE is equal to IBA.
Yeah, so
and is 180 minus A. So we just need to prove NDK collinear.
And so yeah, that would solve it. Yeah, if we can show ND and K are collinear, that would solve it. I wonder if we even need that though. ND. So NDL. So I'm thinking NDL, it's 360 minus N. Yeah, let me see if I can show those are collinear. So NDK. Let's see.
Is ND parallel to AL or something?
I don't think so. No, because MN is parallel to AL.
Oh, yes.
Um, so yeah, we want to show NDA is equal to ACB. And ACB So yeah, if we know, yeah, there has to be like a simple solution to this problem, it feels like. So like I'm wondering maybe the radical axis theorem. Let's see. Can we show AOND is cyclic?
Does inversion around D help by any chance? Because we have so many circles through D.
Yeah, we have a lot of circles through D. Let's see. Yeah, inversion takes a long time to do in GeoGebra. That's the only reason. Yeah. The Dumpty point does solve it almost immediately. Yeah.
Should we try proving that AKD is equal to AKN?
We could try that. AKD is equal to AKN. So AKD is equal to ACD. Is ACD similar to AKN?
Yeah, basically we cannot relate N to the diagram.
Well, if ACD is similar to AKN, that means that ADN is similar. Oh, but wait, N is the midpoint of AB, and we want to show D is the midpoint of AE, right? So if we could show ND is parallel to BE, that would solve it, right? It kind of like that.
Yeah, but that again reduces to proving NDK collinear. Because if NDK are collinear, then angle ADK is 180 minus C, which says NDA is 180 minus C, and we know BEA is BEA is equal to C.
You know what? What if we flip the problem around? So, like we start with a cyclic quadrilateral ABEC, right? We take a homosity of ratio half, so we get ANDL, and then we want to show the circumcircle of ADB is tangent to AC. That seems like it has to be doable, right? And it's probably just an angle chase.
We can maybe remove these points. Remove the circles basically.
Yeah, hold on just a second. Yeah, this isn't, it feels like an easy problem, right? So ABEC, you start with that cyclic quadrilateral, you just dilate it by a factor of a half. So you got ANDL, and you just want to show the circumcircle of ADB is tangent to AC, right? That should be, which is the same as saying, I mean, so ABD and AEB, huh? Hold on a second. Yeah, I just want to, I want us to find the best proof that uses like the least stuff. So okay, so we want to show BD and BC are basically isogonal. Yeah, we want to show BDA is similar to BEC. BDA and BEC. Is it true? Yeah, how do we show BDA is similar to BEC? Okay, I think I might have an idea here. BC over CE. It's half AE. And
I think this NDK collinear is an angle chase. Like we can try proving that NAD is equal to AKD.
NAD.
NAD equal to AKD.
AKD. Do you mean NKA is equal to AKD?
NKA is equal to... No. We know that NA is tangent to the circle. So NDK should be collinear. means that we can apply the angle property of the tangent, that angle contained in the segment is equal to angle subtended by tangent.
You're saying you can prove, so you're saying you have a proof that ND and K are collinear.
Yes.
So how do you prove that?
We angle chase NAD in terms of, we write it as FAD minus FAB, and FAB can be written in terms of AFB.
Okay. So we would have NAD, right? NAD.
N is equal to FAD minus FAN. And FAN is basically 90 minus angle A, because we know FAC is 90. And
so I get that we can calculate angle NAD. How does that show that ND and K are collinear?
we can also calculate angle AKD.
AKD. Okay. So NAD and AKD.
Well, yeah.
So angle AKD. Well, angle AKD is automatically equal to angle NAK.
No. AD is equal to AKD.
So
You can just construct the segment NDK and verify that NAD is equal to AKD.
yeah, so NAD is equal to AKD automatically, right? Since NA is tangent, right?
Yes.
I guess, yeah, we don't even need to do an angle chase. Angle N, or I mean, it's immediate, right? Angle NAD is equal to angle AKD, right? See what I'm saying?
Okay. I think I wanted to prove that NA square is equal to ND times NK.
Okay.
To show some similarity and then prove that NDK collinear, but wait a second.
There's just so much structure going on. Yeah. All right. Let me try something else. So oh, hold on a sec. I think I got this. So angle ABD is equal to angle DAC. Yeah. No, I feel like we got this. Yeah, hold on just a sec. I think I had it. But yeah, we can show ABD is similar to BEC very easily.
We need to show that DBA is equal to EBC. Well, that seems chaseable. Yes, DBA is half of DFA, which is half of DFA means 90 minus FAD. Do we know FAD?
I think I have a pretty nice solution here. So I'm gonna write it out. So here's my idea. We can actually delete a lot of what's in this figure. So Yeah, we don't need N, L. Whoops, what did I just do? Yeah, we don't need that. We don't need this. We don't need this. So I can show that both BDE and CDE are similar to triangle ABC. And that is just an angle chase because well, okay, so first I'll do it this way. So yeah, I didn't show BDOC as cyclic yet, but I will. So first I'm going to show BDOC as cyclic. So actually, you know what? I don't even need to do that. I'm just gonna
We can angle chase BDE down in terms of angle A, I guess.
yeah. So we have angle BAD is equal to I had this. I'm sorry.
I mean to angle chase angle BDA.
Oh, let me do this. So angle DBA is equal to angle DAC is equal to angle EAC is equal to angle EBC. Whoops. And then also angle BAD equals so BDA is similar to BEC. And then by properties of spiral similarities, that means that BDE is similar to BAC. All right. And then also CDE is similar to BAC. I think a lot of people left. Oh no, Hakan's still there. Hakan and Enrique are still here. Sorry. Yeah, thanks for bearing with us, Hakan. Yeah, sorry we didn't do your solution using more theory, but yeah, I just wanted to do this one. So BDE is similar to BAC, and then we also have EDC is similar to BAC. And basically, once we know all that, those two mean that DE is the angle bisector of BDC. Whoops. And once we know it's the angle bisector, basically, yeah, we want to show like a harmonic conjugation. So I guess once we show BDOC is cyclic, it's not hard to show that OD is perpendicular to it. So I'll say let OM intersect BE at K. And then we have since BK bisects angle BBC and OK is the perpendicular bisector of BC, then that means that OB, that means that BDCK is cyclic. And then can we show O also lies on that? It shouldn't be too hard, right?
We already know BDOC is cyclic.
Yeah, we know that because angle BDC is equal to 2 angle A, because those two triangles are similar. So that means that BDOCK is cyclic. And then OK as a diameter implies angle ODE is 90. So and that means that since OD is perpendicular to AE, then D is the midpoint of AE. All right. All right. So I will move on to the next one, but thanks everyone for your input, and I will read more about Dumpty points. Yeah. All right.
Yeah, and one can also show that angle ODA is 360 minus BDO plus BDA, and those are directly following from those those similar triangles.
Yeah. So once we know, yeah, angle BDE is angle A, and angle CDE is angle A. Did we even need these similar triangles to show that?
Yeah, we needed similar triangles to calculate angle BDA, I guess.
Yeah, we did need those similar triangles.
Oh, wait, BDA was already known to us without those similar triangles. And BDOC was also proven so earlier.
Yeah, we could have. I don't even think we needed similar triangles necessarily, because BDA is basically 180 minus half of AFB, and
Half of AFB is just AFO, which is angle A.
yeah. Oh well.
Means that we just needed to show that BDOC is cyclic.
Yeah, those are all properties of harmonic quads. All right. So I will move on to the next one, but yeah, I'm sure there's, yeah, this problem doesn't look like the solution should have been that hard. So triangle ABC, B is the midpoint of BC. Let's see. The bisectors of ADB and ADC. Okay, so we draw the circumcircles, and then we draw the angle bisectors. At E and F. I wonder if EA and F are collinear. I don't think so, but yeah. But we want to show EF is perpendicular to AD.
Our angle BAC looks like 90. Should we change it?
Yeah, I'll go change it.
Yeah.
Only more like that. Okay. So we want to show EF is perpendicular to AD. So E is the midpoint of arc AB, F is the midpoint of arc AC. So the line, yeah, I wonder if, let's draw the centers of those two circles. So so we know GH is perpendicular to AD, right? And E,
If X is the other point, concurrence point of circumcircle of ABD with DF, is EGX collinear?
possibly.
They do look like collinear.
Oh,
No,
I don't.
I mean EGI collinear.
Oh,
Yeah, they are collinear. Similarly for the other side.
yeah, because of the right angle. But yeah, whoops.
Yeah, that's a right angle. So should be.
Yeah. But I think so GH we know is parallel to AD. Oh, it's all right. So GH is parallel, and we want to show EF is parallel, and G is the midpoint of IE, and H is the midpoint of JF. It feels kind of like the gliding principle. So we have two midpoints, and B is also a midpoint. So what if we look at the triangles BEI and C? So BEI and CJF. And we apply the gliding principle. Well, no, it would be B.
We can draw perpendiculars from E to AD and then compute AX by AD XD.
So
and both of them are similar.
So you said AK over KB, we could try to calculate that?
Yes. Yeah, we also know that EA is equal to EB.
Yeah, EA is equal to EB.
No, I mean, we could use it in calculating AK.
Okay, so yeah, so AK, it's kind of like AE cosine of EAB, right? Which is BE cosine of EAB. Yeah, we also want to use angle EDF as a right angle, right? So
And we also haven't used that D is the midpoint here.
yeah. So yeah, there's a lot of information. I think I might be able to trig bash it the way you said. Let me see if I can convert this into like a synthetic proof. I'm gonna go write it up. So AK, that's AE cosine of EAD. And that's BE. EBD. Which is, so EBD, that's half ADB. Let me draw these points here. Is ML parallel to BC? Yeah, I think ML is parallel to BC. I think that might help us here. That's by the angle yeah, so by the angle bisector theorem, ML is parallel to BC. Is ELMF cyclic? Yeah, okay. I think it might be those two things. So, so yeah, ELMF, maybe we can show that's cyclic by power of a point, or I don't even think we need that. Yeah. All right. All right, so I'm going to start typing it up. Did we even need points G and H? I don't think so. So let DE meet AB at L. Right. And then, so we have AL over LB. here's where we use that B as the midpoint. So AB over BC, which is equal to AM over MC. And so that means that LM is parallel to BC. And then I think now we can just use an angle chase to show that ELMF is cyclic, because we have angle MLD is equal to angle EDB, which is
EDB is equal to EDA because of angle bisector.
yeah, EDB. So yeah, could we use power of a point to yeah, I'm trying to think how to show ELMF is cyclic.
Yeah, if we let the intersection of LM and ADB something.
Oh yeah. Okay.
Yeah. Then we know that angle ALG, some angle we proved right now. Yeah, GLD is equal to ADL.
GLD is equal to what?
ADL.
ADL. Yeah, because this is a right triangle, right? So.
And we can compute DL from this. That DL is equal to root DG times DA.
Okay, so DL is DG times DA.
If we want to apply power point, we need DL also here.
Yeah. I think we could just back, because DL times LE. I mean, triangles DLE and ALE are similar, right? So, well, what if I just kind of write it like this? So, well, but yeah, we want DL times DE. So.
Wait, we can write DL times DE as DL times LE plus DL square.
Yeah.
And DL times L is equal to LA times LB. And DL square is DG times DA. And I guess we can prove it constant from the other side too.
DL.
Because
so right. So
we wrote that DL times DE is equal to LD times LE plus DL squared.
all right.
We substitute DL times LE from power of point for L, and DL square should be DA times DG.
What is DL squared?
DL square, I guess we should get it from similar triangles in ALG and ALD.
Okay, so
DL square equal to AD times.
are they similar then? Let's see. So DL squared is AD times DB minus AL times LB. How do you get to that? I guess we could just use the formula for the length of the median, right? Yeah, so.
Yeah, that finishes us off because we can cancel BL times LA. And we know that DA times DB is DA times DC.
Okay, so is equal to, I'm just writing it out, AB squared times.
Yeah, cosine law in both triangles, I think can derive this formula.
Okay, so basically, I think this is like Apollonius's theorem, but we have basically AB squared plus AC squared is equal to 2AD squared plus 2BD squared, I think. I think that's it. This is probably equivalent to what Hakan said. Okay, so but that, okay, so that gives us AD, wait, but not DL. So
Yeah, we are calculating DL as by Stewart's theorem in triangle ADV. We know that.
Okay, so we're using Stewart's combined with the angle bisector theorem.
Yeah.
Okay, so basically Hakan is giving a formula, yeah, for the length of angle bisector. So yeah, I'll just write it. So I feel like there should be a nicer way to do this though than Stewart's. Let me see if there's a better way to show that that's cyclic. Yeah, it works, but I want to see if there's a nicer way we can do it. Is the circle of ELA tangent to? No, it's not.
Circumcircle of GLA would be tangent to LD.
Okay. So if we draw that circle, it's tangent. If we draw this circle, it's tangent. Are you sure it's tangent? Let's see. No, it intersects it. So yeah, we want to show ELMF is cyclic. I feel like I think that's equivalent to showing BC is tangent to the circumcircle of EDC. Let's see. And then we could use like Rimes theorem. So so what's the center? Let's see. Yeah, I'm trying to solve it without Stewart. Yeah, we're trying to yeah, do it without the formula for the length of the angle bisector. I think there has to be a way without it. let's see. So, I mean, if we let AD meet that at H, can we show that HGMF is cyclic? And then we could use the radical axis theorem.
Is AL parallel to HEA?
Is AL parallel to what? Oh, HE? Could be. The no.
Oh.
HFD isn't 90. That would be pretty interesting. Let's see. No. So yeah, if we can show DL times DE is like something squared, I think that would help get us there, right? So we want a circle.
I guess we have to use the.
Oh, you know what? You know what? I think we might be able to do it like this. So DL times DE is DB times it's DB times DH. And I guess this configuration kind of looks familiar. So that's kind of why I thought about it. But can we show DH equals DI? I don't know if I made it easy or not, but so yeah, we want to show angle HAI is 90. So can we show DH is equal to DA actually? So really DB, we want to show DB times DA is DL times DE. This is like a lot of interesting stuff.
I guess we can use Ptolemy in the triangle to compute the diagonal DE. We know all the other things because EA is equal to EV. I think that.
Oh, because EB is equal to EA. I keep forgetting that. So yeah, I think.
Yeah, and it's a result too that one can compute the diagonal by knowing the four sides of the cyclic part.
So yeah, so we have DB times DA is DL times DE. That's kind of interesting, right? Okay, so Just thinking how to show that.
This means that DBE is similar to ALD.
DBE is similar to ALD.
ALD. Yeah, that's
Yeah.
it.
Yeah.
And I guess yeah, and okay.
Yeah. Okay. So.
Yeah.
Yeah. Okay. So that similarity really kills it. Yeah. All right. So. Yeah, I don't even think you need these guys. So I'm gonna write that out. Okay. So. There's so much stuff going on. It's hard to manage in my head all at once. But basically, yeah. So we have angle EDB is equal to angle ADL. And angle BEB is equal to LAD. So that means those triangles are similar. And then that means that BD over DL is equal to BE over AD. So that's LD over 80. And then that means that, yeah, so that means that BE times DL is equal to BD times 80. And then similarly, DM times DF is equal to CD times AD. Implies, I'll say equals BD times AD. ELMF is cyclic. I can see the 5 comments. That's okay. So let me draw that. Yeah, if only every problem on the IMO were, yeah, that would be awesome if Mario were here. Yeah, he would solve all these super fast. So once we know ELMF is cyclic, it's just an angle chase.
Just an angle chase.
Thanks for writing that in LaTeX. I appreciate it. All right. So then angle EFM is angle DLM is 90 minus angle GMD, which is 90 minus angle GDM. And so AD is perpendicular to EF. I like it. There we go. So this is the last problem I chose for today. We can take a look at one more if you guys want. Let me see if Irajan is still on. I was going to do his. Yeah, let's do one more for the last 15 minutes. So is Irajan still on? So he gave me a problem. So I'm gonna do it. Sorry. So here is his problem. So we have a triangle ABC. Actually, hold on. Let me take it from Discord. So I'm going to paste it in. Discord. Sorry. Let's see. Copy. There we go. So I did not LaTeX this yet. There we go. Okay, so we have an isosceles triangle. Let's call this C. And that's A and B. M is the midpoint of AB. Whoops. Oh no, M is not the midpoint of AB. We want AM is equal to 2BM. So I will have to trisect it somehow. What's the best way to trisect? Let's see. So I'm going to trisect in kind of a very lame way. This is my way of trisecting. Whoops. Oh, yeah, okay, too late. But yeah, next time I'll do it that way. So, actually, so yeah, this is M. But yeah, no, I've seen Evan Chen use vectors before like that. That's probably the better way to go. Okay, so AM is 2BM, F is the midpoint of BC. And H is on AF, such that HM is perpendicular to AF. That's H. And then we draw the parallel to AB that goes through C. And it intersects BH at X. And we want to show AX is tangent to the circumcircle of ABC. Let me erase some stuff. Hide. Okay. So, all right. The Samedian, okay, so, I mean, since angle A and angle B are equal, showing its tangent is the same as showing that AC is the angle bisector, right? I guess there's a couple of equivalent ways to think about it. So, yeah, it's kind of like, we could try to show that this is a harmonic quadrilateral, right? B, C, G, A. Oh wait, what did I do? HM Oh yeah, okay. HM is perpendicular to AF. Is GABC we want to show it's harmonic, right? Can we project through H or something? Let's see.
I guess this should be something like angle. We know that AF is the median, so angle GAC has to be equal to angle FAB if the result is true. And we know that GB is perpendicular to AC, so we might want to prove that angle GAC equal to FAB, or HMA is half of AGC or something like that.
So yeah, I think
we don't need X here. We just want to show that these angles are in these.
The very center. Yeah, so yeah, I think we can show XAHC is cyclic. Well, yeah, how do we know that actually? Yeah, write out some of what you were thinking in the chat. I think it worked. There's just so many like ways to think about this here. But yeah, AC is not, I don't think AC is perpendicular to BX, right? That's one thing that's been, yeah, those are not perpendicular, they're just closed. So yeah, so AM, is HM parallel to AX? Yeah.
Can we please remove circumcircle of ABC for a second?
Yeah. But yeah, I want to use projective geometry since
we know that AF, we see that HM is parallel to AX because, wait, that would be in the case if A, B, C, X is a parallel.
Is HM so I think HM is parallel to, oh no, not necessarily. I don't know if any of these three are parallel, are they? Is MJ parallel? Yeah, no, they're not parallel. None of them. I think they might all concur at a point. Let's see. No, they're not parallel, and they, yeah, don't.
The 1:2 ratio also reminds me that in a parallelogram, if you connect points to opposite midpoints, then it trisects the diagonal.
It trisects the diagonal.
But yeah, there are no parallels here, so might not.
So let's see if I could use Menelaus. So if let's CH meet this at a point. Oh, actually, you know what? Yeah, let me add in some stuff. Yeah, you just have to figure out how to use all the different conditions. Maybe you can add the other trisection of AB. All right. So let me do it this way, kind of the lazy way. Okay. Yeah, so we want to show AHCX is cyclic.
Yeah, isn't X the centroid of ABC?
Is H the centroid?
Just asking. Is
Oh,
CH all perpendicular to AB? I mean.
I don't think so. Let's see. No.
Yeah.
So BX is a symmedian.
We should add the B median here too.
Yeah, let's see.
And move the diagram a little.
Yeah. Whoops. Do it like that. Okay, that's better. It's hard to get a good diagram, but just leave it like that.
Are BLJ collinear? Well, don't look so.
No.
No.
All right, so yeah, like if we could show.
Yeah, what we want to show is that LBC equals XBA, which equals BAC. So
LBC.
I think we can go similar triangles here. But
all right, I'm going to leave it to the viewers to finish it just because we've run out of time. But thanks everyone for participating. Yeah, this was a fun session. So I'm going to read up more on Humpty and Dumpty points. And I think that'll be it for today. So if you like this video, like and subscribe as usual, and I will see you next time. Take care. Yeah, maybe next time we'll solve it on the chat. See you next time.